If one implements the PID controller in the analog domain, then normally op-amps are used to implement the PID controller circuits. Let us look at some typical circuits. So first the block diagram to have a reference. So this is the reference, and this is the feedback, plus and minus, error. So one path leads through Ki, integrator, and another path leads through Kp, the proportional part, and then the differential part, which is Kd, followed by the differentiator d by dt. All these three will get summed up, and the Vc is the sum of the integrator action, the proportional action, and the differential action. So let's see if we can implement this using op-amps, the reference and the feedback. So let me take an op-amp, the VCC, VEE, plus and minus. Let us implement this first. So this is a difference amplifier. So let me draw the difference amplifier. This is two resistances. You can have equal resistances. All are equal resistances, so that you get difference of these two. If you have ref and feedback here, then E, which is equal to ref minus feedback. Then the output of this goes through these three paths. So let us mimic that. I'll take one op-amp, VCC, VEE, plus and minus. I will ground this, and I will take, in the inverting amplifier mode, an integrator action. So I'll have a resistor here, and I will have a capacitor here. And this is an integrator. This is a C. So 1 by SC on the feedback path side, and this is R. So 1 by SCR will be the total gain, and 1 by S is coming into the picture, that is the integrator action. And 1 by S and 1 by RC will be the Ki part. So this is the integrator action. Then I will have one more op-amp, and let me do the proportional gain action. So I'll just put an inverting amplifier with a fixed R1, R2 gain, and this will give you the proportional action. And the third is the differential action, and I'll put a capacitor here, 1 by SC here, and a resistance here, which will give you the differential action. Actually, the dual of this integral action. So I will have a resistor here and bring it out, and use one more op-amp and do an inverting summer. So I will join them up together and then put a feedback resistor here, so that this will act as an inverting summing amplifier. This will be VC. So this is C1 and R1. So here you will have 1 by S R1 C1 with a negative sign, because this is in the inverting amplifier topology. Here this would be, if this is RP1 and RP2, so minus RP1 by RP2 will be the gain of this. So this is the Kp value. And if this is R3 and C2, then R3 divided by 1 by SC2, or R3 C2S will be the gain of, minus of that will be the gain of this differential amplifier. And you see that this is the idealized gain. This is not the actual gain. There is the op-amp acts as a low-pass filter. So which means that there is a pole. So there is a pole that comes in. So this is not actually, as I am showing it here, just a numerator 0 at S is equal to 0. there is a pole at the denominator, which will make it a practically realizable circuit because the op-amp is having an internal pole. So some especially you can look into the data sheet for the exact location of the pole, which will give you the op-amp low pass pole. Now all these three add up to give you the integrator action in this path, the proportional action in this path, and the differential action in this path. So this circuit is a PID controller circuit. Now here across the C, I will put a clamper in the form of two back-to-back Zener diodes. So let us say that at the output, which is going as a control input to the PWM block or plant control input. So if you say that the plant control input or the compare for the PWM triangle limits are, let us say, plus minus 5 volts, just like as we discussed in the anti-wind-up. I can set the Zener diodes here to be plus minus 5 volts. Capacitor C1 is the integration element. This is the memory storage element. And the moment the capacitor value hits whatever the Zener breakdown voltage plus 1 diode drop, it will clamp to that value. It will not integrate any further. That is where the wind-up action is stopped. And once the error comes down, the capacitor will come into the control band immediately. So this back-to-back Zener diodes form a very nice anti-wind-up clamp action or clamp circuit for the analog version of the PID controller. Let me now go down a bit and simplify all this. Okay, let me draw a PI controller with just a single op-amp. So let me draw an op-amp here, plus and minus, plus I am grounding, minus. So in an inverting mode, so you have a resistor here, have one more resistor and a capacitor, connect it like this, and this is error, R1, C1, this is R2, putting the VCC and VEE, this is V0. So what is V0 equal to? So V0 is equal to, so this impedance divided by this impedance, minus of that. So E into minus E into this impedance is R1 plus 1 by SC1 divided by R2. So this is your V0. Now if I simplify it, so you have SC1R1 plus 1 divided by SC1R2. So further I can simplify it, R1C1 by R2C1 into S plus 1 by R1C1 by S. See that integrator action there. I can further simplify this as minus E into R1 by R2, which is like Kp gain, and S plus 1 by R1C1 is a 0, and you have the integral action S is equal to 0. Pole at S is equal to 0. You have 1 0 at S is equal to minus 1 by R1C1. So this formulation is in the form of a PI controller. So this is a single op-amp PI controller. There is a negative sign, so you can include after this one more inverter, a unity gain inverter, to see that the 180 degree phase shift is removed. So include an inverter post the circuit. And like before, I can have two back-to-back Zener diodes to act as anti-wind-up clamp. So this is the anti-wind-up clamp. So this is a PI controller. So this PI circuit can be converted into a PID circuit, same single op amp. I will put one more summing point element here. So let me add one capacitance and series resistor. Call this R3 and C2. Now this is coming at the summing point junction. So we had this gain as given here. To that I add this particular gain. So this is the same error that you will give. So let us look at this, the gain. So R1 plus 1 by SC1 is in the numerator, and the denominator, this impedance is R3 plus 1 by SC2. Now with a negative sign. So this is equal to S R1 C1 plus 1 divided by S R3 C2 plus 1. So this would be the transfer function for this part. So this and this gain will add up here. So that will get add up here. So you will see that there is one integrator pole, and then there is another pole which is at some finite point in the S-plane. Left of the S-plane, you have 1 0 here contributed, and then there is another 0 when you add it up. So you will have two zeros coming in there, and one integrator pole and one another pole. So this will be in the topology of, in the format of a PID controller. So you can accordingly design the various R1, C1 resistances and capacitances to map to a design similar to this, or to map to the frequency plot that we had discussed and plotted while discussing the operation of the PID controller. So in this way, in the analog domain, using op amps, you can have PID controller circuits. Several PID controller circuits are there. These are a couple of examples which I presented. Several of these systems implement the PI controller algorithm within a microcontroller in the discrete domain. So it is important for us to have a look at the discrete PI implementation. So for that, let me first draw the block schematic. So you have the reference, have the feedback signal, the error passes through the Ki, the integration block Ki, and I have a summation, and z to the power of minus 1, which is feeding back the output here. So this part is an integrator. So we have seen that this part is integrator. It's one of the forms of integrator. This is the accumulator. Recall yk, which is fed back, this yk minus 1, so that keeps getting added up, plus the delta area. There are different mechanisms. One of the mechanisms is where ki is t, so whatever the input stream multiplied by t, the value of that input stream multiplied by t will give you the backward integration rule. This is one such algorithm. But there are so many algorithms like trapezoidal rule, the Simpson's rule, Runge-Kutta rule. All this will come here, will modify here in the algorithm for finding the delta area. So I am using the simplest algorithm so that it can be easily understood. So here is the integration output. So that needs to be summed up with the proportional part. So I have Kp, the error is taken through the Kp, and both the integral output and the proportional outputs are added up here. So after adding, I will put one more summer here in case one wants to add any feed forward term, because remember that in the controller, in the small signal control, the controller handles only small signal. So this will be a small signal value, and to the small signal value you need to have the steady state value, and that would be the feed forward term. So you add them, then together the small signal plus the steady state value will form the control input, which can go to the plant, but you may have to pass it through a limiter first to see that whatever value you get here does not exceed this max limits, extreme limits, which are Vmax and Vmin. So this will be Vmin, let's say this is Vmax, so this is a limiter. So output of this limiter can be the compare signal for the PWM triangle or the timer. Use this to compare with the PWM timer. So this could be the duty cycle signal, which can compare with the triangle and provide a pulse width modulated signal. So the algorithm for this is your VC. This is VC. Reference, feedback. I'll call this a VCI. This is VPI. Summation of both this. This is feed forward term. I can make this also blue and this also blue. So the algorithm is simple. You can just look at the block diagram, start writing. E is nothing but ref minus FB, feedback term. Then let us say the integrator. So before I write the integrator, I am going to include one more block here for taking care of anti-wind-up. Now this is not a summing block, this is a product block. Remember, this is a product block, and I will give in a variable k clamp. So I'll explain. If k clamp is 1, so whatever input is passed on to the accumulator and accumulates in a normal fashion. If k clamp is 0, whenever you want the anti-wind-up action to come in, then the input error is not passed through. This will keep staying at whatever the previous value is. Accumulator will not accumulate any further because this will be 0. So this will become your anti-wind-up part of the algorithm. So if Vc is less than Vmax, it is in the control band, and also that Vc is greater than Vmin, which implies that Vc is in the control band, then I want k clamp to be 1 such that the input signal is passed on to the accumulator. Else, I make k clamp is equal to 0, which means that when Vc is falling outside of this control band, you make k clamp is equal to 0. So then VCI is nothing but VCI is equal to VCI plus k clamp into ki into e. K clamp into ki into e. So this will be the integrator output. So if the VC is in the control band, k clamp will be 1 and it will be acting as a normal integrator. If VC is outside the control band, k clamp will be 0. There is no accumulation. This part is 0. So VCI will be equal to VC. It will take the previous value and continue to stay there. Now this part is Kp into E. So VPI. So that is accumulation, and this is our anti-wind-up variable. So VPI here is VCI plus Kp into E. And what is given to the input of the limiter is VPI plus feed forward term. So I will put this condition: if VPI plus feed forward is greater than Vmax, then VC is clamped to Vmax. Else, if VPI plus the feed forward term is less than Vmin, then VC is clamped to Vmin. Or else VC is equal to VPI plus feed forward term. So this will give you the output of the controller. This output of the controller can be given to a PWM block here. So let me draw a PWM block, and output of the PWM block will be the pulse width modulated pulse signals. So this VC, which is coming from the controller, can become the duty cycle variable, and this duty cycle variable can be used as the compare value to compare with the timer value inside. And if you use the timer 0 counter of the ATtiny, you can use it to compare with the timer 0 counter, and the output will be pulse width modulated wave shape like this, where you could have one edge getting modulated based on the value of VC. So this is the pulse width modulation signal. So this entire algorithm is the control algorithm where input is E and output is VC. So VC is what is returned. So make this whole thing into a function and call it in the ISR routine as a control function. If I open the platform IO editor within the Visual Studio Code and look at our generic application template program. So in the main.cpp here, where you are having the ISRs, the various ISRs, the interrupt vectors. In the ISR timer 0 overflow, we had written some part of the code, right? We had set duty cycle as a constant. So the duty cycle can be the outcome of the PI controller action. So for example, I could say that duty cycle, instead of being constant, it could be output of a PI controller. So let's say PI controller, and to which I am passing reference and the feedback signal. Let's say as an example, saying the template for PI controller. So I pass reference and the feedback value, and this feedback value is coming from the ADC. So let's say it is coming from the filtered ADC value, and use these two to generate the error within the function and get the value of VC, and VC will be the duty cycle, and duty cycle will be fed to the PWM block, which will give you the PWM signal. And this function needs to be created. So go into the source folder, open mypicontroller.cpp, a new file, and within that type the function and with the algorithm that we discussed for the discrete PI implementation. Then after that, go into the myfunctions.h and define the profile of the function that was created in the source folder. So then you will have the PI controller also getting reflected here. So I will leave this as an exercise to you so that you can update the generic application program with one more added function, which is the PI controller function.